Then we'll talk about the logarithmic dependency on uncommuted kinship and whether it belongs or not, in which case it belongs or it doesn't. Right? So let me start by recalling uncommuted kinship. Right, so this is non-commutative kinship. So we had matrices A1 through AN, right, D by D, symmetric matrices. Remember, here symmetric means that the matrix is the same as its transpose, right? Not symmetric as the random variable being the same distribution as minus the random variable. Okay, and so these D by D symmetric matrices, the statement was if we have Gaussian random variables, so G1 through Gn, all of them M0, 1, IID, the following held that the expected value of the spectral norm of this Gaussian series, right, GK, AK, was smaller or equal, and here I'm not going to care about constants for now, smaller or equal than logarithmic factor on the dimension times sigma, where sigma was this variance parameter. Right, so sigma was the spectral norm of the spectral norm of the sum of the AK squares. Right, this is basically the spectral norm of the expected value of this series squared. Right. And so now the question that we're interested in today is, does this belong? Right, is this needed? Right, we saw that sigma is needed because basically sigma squared is the, right, so you can write sigma squared as just the spectral norm of the expectation of x squared. Right, and we expect, we know from say Jensen that this is for sure, this is smaller than the expected value of the norm of x squared, and that should be roughly the square of this because of concentration. And so we really expect that the sigma is needed. The question is the logarithmic factor needed? So let's try a few examples, right? Examples of things we know. Okay, so let's start with example number 1. Let's start with Wigner matrices. Right, so Wigner matrices, let's remember, W is a Wigner matrix where the entries Ij were all IID and 0, 1s. Right? And the matrix W is symmetric. And I mean, if you wanted to normalize things exactly right, then in the diagonal you should see something with variance 2. Right? This is so that you have rotation invariance. Okay, I mean, for the sake of the spectral norm, nothing really changes, but this is the right object. Okay, so let's see. So this matrix, right? We can write it in that form. We just have to make, the following matrices. So we take pairs of Ij with I smaller than j. Right, so let's take pairs Ij, ordered pairs. Let's say I say smaller than j. Then we just make the matrix A Ij, right? Be Ei Ej transpose plus Ej Ei transpose. Right, so this is the matrix with the 1 on the entry Ij, and then 1 in the entry Ji, and 0 everywhere else. And when I is equal to j, we just have to make square root of 2, right? So that we get the right variance of Ei transpose. Right, so this is just a matrix with, the 1 or square root 2 on the diagonal entry I and 0 everywhere else. Okay, and so now, right, we have that the Wigner matrix is clearly equal to, right, the sum for all I smaller or equal than j of these Gaussian random variables Gij and this Aij. Right, we can write the Wigner matrix this way, and now we can ask, okay, let's use non-commutative kinship and let's see what non-commutative kinship gives us. Right, this is now a natural question to ask. Okay, so let's see. So what is the sigma? Right, so let's see. Sigma squared is what? Is the spectral norm of the sum of I smaller than j, smaller or equal than j, of Aij squared. Right? So let's see what this is. Right? So okay. right? But what is not a square here, right? What is aij square? So in the instances where I is the same as j, this is a matrix, right, that had a 1 in entry I, or a square root 2, so when you square it, there's a 2. For any other of these matrices, you get a 1 on the entry ij and a 1 on the entry ji, right? There's basically a 1 here and a 1 here. When you square it, what you get is a 1 here, 1 here, 0, 0, right? And so basically, this matrix is clearly going to be diagonal, right? Because all of the squares, aij squares and ai squares are going to be diagonal. And the amount of stuff you get on an entry ii is you get a 1 for each time it shows up with another j, which is d minus 1, and the 2 for the diagonal element ii, right? And so what you get here is exactly, right, I mean, if we write it, you get d minus 1 terms coming from the off-diagonal parts of aij plus 2, right? And so you get this times an identity, because each entry in the diagonal is going to be exactly d minus 1 plus 2. Right, and so the spectral norm of this clearly is d plus 1. Right? And so we have that the spectral, the sigma parameter is exactly square root of d plus 1. Right? So let's use another color to write over there and see exactly what an encryption would give us. Right? So what we have is that then sigma, the sigma parameter here, is d plus 1. So we would say that the spectral norm of the Wigner, right? What would non-commutative kinship imply? It would imply that the spectral norm of the Wigner is small or equal then. What do we get? We get square root log d times square root d. Right? Because we get the d, I mean the d plus 1 and the d up to constants are exactly the same, and we get the square root log d from here. Right? And so clearly this is not optimal. Right? Clearly here, the square root d log d doesn't belong. As we saw in the previous class, the right value for the spectral norm of the Wigner is indeed just square root d. It is 2 times square root d. And so this term here doesn't belong, right? So in this case, so for Wigner, the square root log d does not belong, right? It's suboptimal, right? So for Wigner matrices, right? For Wigner matrices. This is suboptimal. Okay, so for Wigner matrices, this is suboptimal. Right, so now, in particular, the log d factor doesn't belong, right? The right answer is something like sigma. So now we can ask the question, is this always the case? Do we actually need the log d factor, or is sigma always the right answer? Right, this Jensen argument that sigma is a lower bound is actually completely tight in the sense that sigma is just plainly the right answer. Just let me give you another example where that's not the case. Okay, to show that the logarithmic factor does indeed belong in some cases. Okay, so let's now try a different example. And the example I have in mind now is a diagonal matrix with Gaussians in the diagonal. So 0 here, and n0 1s in the diagonal. With 1s, IIDs, and diagonal. Okay, so this is now, I mean, this example is sort of special. Everything is commutative because every matrix is diagonal that's going to show up. But it's still an instance of this, right? So let's see what it gives, right? So in this case, what we have that the EKs are simply EK transpose, right? For K course from 1 to D, right? So they're just, right? If I now take the sum of GK, AK, K from 1 to N, to D, right? Then what do I get? I get a matrix that has a G1 here all the way to Gn. Okay, so now what's the spectral norm of this object? Right, the spectral norm of this object, right, what do we know it is? It's just the max, because it's a diagonal matrix, that the maximum absolute value of the diagonal elements. So it's just the maximum for K right, from 1 to D of GK. But now we know, if we have n D Gaussians and we take the maximum, we know what the value of this is, and the value of this is around square root log D. Right? This is a very nice calculation if you haven't done. I mean, it comes from the fact, so I'm taking more and more Gaussians of variance 1, so eventually the largest one will get bigger and bigger. Right? And the deviations for the Gaussian, the probability that you see a really large number should be something like e to the minus x squared, where x is that number. Right? So the probability of seeing a certain number, say square root of log D, should be something like e to the minus the square of this, so e to the minus log D, so it's roughly 1 over D. So that you have D things, so you expect to see things with that kind of probability, right? So this very, hand-wavy argument already gives square root of log D, and this can be, of course, made precise. By upper bounding, by union bounding, and to lower bound, you need to work a little harder, but it's also not so hard. But let's see what non-communication gives us. Right, non-communication, okay, what is sigma? Let's see, what is sigma squared? Sigma squared is just the sum of the squares of these matrices, right? The spectral norm of the sum of the squares of the AKs. But AK is a matrix just a 1 in the diagonal, 0 everywhere else, so the sum is just the same matrix again. So this is really just the spectral norm of the identity. This is just 1. Right, so non-communication gives that the expected value of the spectral norm of the sum of GKs AKs is smaller or equal than square root of log D times sigma, which is in the case is 1. Right, so here it is correct. Right, here the logarithmic factor does belong. Right, it is optimal. Okay, so we know that we can't remove this logarithmic dependency every time. Right, it is needed in general. Right, it is needed in general. Right, so this is needed in general. It is needed in the diagonal case. But now it raises then, we know, but on the other hand, for the Wigner case, it gives quite a terrible result, right? If you looked at the tail bound we derived, and you look at the probability of the spectral norm of the Wigner being something like square root log D times root D, will be really, really tiny. All right, and so now the question is, when does the logarithmic factor belong and when doesn't it? Right, so can we have a stronger inequality that doesn't always need the logarithmic factor? Now, as we'll see when we prove a version of this for other Machiavellian variables, as you'll see, it seems to have something to do with commutativity, right? The matrices, the AKs for the Wigner matrix, they didn't commute, while the AKs for the diagonal matrix, they did commute, right? So it seems to have, and in the proof you'll see, it seems to have something to do with commutativity. But there is another kind of argument. This is not a correct argument, but it's sort of an intuitive argument that, what the log D factor is doing is sort of, if you think about what's happening in the diagonal case, it's sort of union bounding over the D possible eigenvalues, right? There's the D because the matrix all commute, the eigenvectors are sort of fixed, there's D possible eigenvalues, and you have to union bound over them, and this is how the log D factor shows up. But as we see from Gaussian concentration, the fluctuations are not measured on sigma, right? They are measured on sigma star. So one possible conjecture would be that the log D factor shows up with the sigma star. Of course, what I'm saying is not quite accurate because in general, when the matrices don't commute, there's not just D possible directions for the eigenvectors. They could be in exponentially many different ways, right? There's just D eigenvalues, but maybe you have to union bound also over the ways the eigenvectors would have to be, and this would get you exponential terms, and it would get you something like a square root D. And in fact, there is an inequality with a square root D and a sigma star, right? Known as a different kind of inequality done basically through some kind of covering number argument, which a union bound like what I'm describing. But one possible conjecture, right? I really, really like this conjecture, is that the fluctuations are measured with respect to sigma star. Right? So let's write sigma star, right? It was the weak variance, which was described last lecture. Right, so this was the maximum over V having norm 1, max V transpose AK V squared. And remember, sigma, of course, sigma was equal to, right, I mean, the spectral norm, so I can write this the same way, right, max V1, right, so, I mean, you could push the V's inside, so you see this is sort of similar, and we saw using Cauchy-Schwarz that it's quite easy to show that this is smaller than this. So the conjecture is the following, or the question: does it hold? Does it hold that okay, so could it be that we can put the logarithmic factor only on this weak variance? And so turns out this explains both the Wigner and the diagonal case. It is known to be true. Known to be true when the matrix, this matrix, when entries are independent. Right, so in both the Wigner example and the diagonal example, the entries turned out to be independent. We know for a fact that this is true in that case, and I'll put references in the notes. Right, but not known in general. So the case of independent entries is sort of very special. As you'll see, if you go in the notes and look at the references, you'll see the proof are there. But this in general is not known. If it holds in general, neither is known any counterexamples. This is one of my favorite questions. If this actually holds or not, and yeah, I think it's honest to say that we really don't know. We don't know very good examples where we can even test it. But so we'll. What I'm going to do now is we'll prove not exactly this, even though the proof for what we're going to prove is essentially the same. We'll prove this with replacing the Gaussians by just Rademacher, by plus or minus 1. So we'll follow a very nice argument of getting to a stronger version of non-commutative kinship, stronger not in the sense of removing the logarithmic factors, but in the sense of allowing, for something that looks a lot more like Bernstein, where the whole matrix is random, it's not just the Gaussian series and so on. And we'll follow a paper by an argument by Joel Traub that I'll add the references in the notes, and the references are in the notes. And I'll start with the Rademacher version of this non-commutative kinship. Okay, and we'll call this sort of the master theorem, and then in next lecture we'll prove we'll start by proving using the master theorem an inequality that ends up looking a lot like, is essentially Bernstein's inequality, just an expected value of the spectral norm version of it. Okay, so we can call this the master theorem for matrix concentration, or Rademacher non-commutative kinship. Right? Sometimes we refer this to the master theorem for matrix concentration. Okay, and it will be the following. Okay, so here I'll use a slightly different notation because it's more classical when talking about Rademacher and variables. Exactly the same, H1 through Hn, right? They're d by d, and nothing changes really if we do Kohler complex. I'm going to keep things real, keep things simple by keeping things on the reals. Right, symmetric, so remember by symmetric we mean that for all these matrices the following is true, almost surely probability 1. And now epsilon 1 through epsilon n are going to be Rademachers. Rademacher random variables. Right, what I mean by this is they are IID, and they are 1 with probability of half, and -1 with probability of half. Okay. And now the claim is the following: that the expected value, it's exactly the same inequality. The expected value of the sum, k equals 1 to n, of epsilon k, each k, is smaller or equal than, now let me get the right constants. We get 1 plus 2 t alpha, so the sigma over sigma squared is exactly the same thing. So this is precisely an Kinchin, but a Rademacher version of it. And so in the next class, we're going to use this inequality to prove statements about much more general sets over in the matrices, and then we'll prove this inequality. The proof for Rademacher and Gaussian is not so different, but this one will be a little more elementary, and I think will be a little easier to see what's going on. And we'll see what motivates, I mean, maybe we'll see a little bit of a motivation coming to this, or why this conjecture should be true in the proof of this inequality. We'll see that this logarithmic factor should show up more when things commute, and when things don't commute is exactly when we expect this quantity to be smaller in a way, so we'll see a lot of this. Okay, but so we'll use this Mestre theorem to prove a bunch of theorems, and then afterwards we will actually prove this Mestre theorem.